Okay, so I have to get to the presentation now. Let's see. Okay, so let me ensure that I have. I think it's okay now. I think. Okay. I have to also ensure subtitles. I don't want subtitles. Mm, okay, subtitles. Subtitles, where do I stop the subtitles? Oh, okay, right there. Okay, I think we are set. So this is a continuation of the history of physics series that we have. So we are right now up to 5 episodes, and what we are talking is very important because. Oh, sorry. Let me get back. Something happened. Let me get back again. So let me get back to that. Bear with me 1 minute. Okay. All right. So, oh, okay. So I think we are okay. Uh, so essentially, it's a continuation. And the question, before I go on 1 or 2 minutes, I just want to recap. The question of physics itself was at stake because physics, I think, went off rails in some ways because of the way things developed. But initially, the episode one talked very clearly about why physics came into being, why it was important. And then the classical physics had a good aspect of the scalar measurements that could be made, and we use that speed, distance, time. These are all parameters we use everyday life, and temperature. And thermodynamics came to being, and temperature, things like that. But the classical physics had the problem of ultraviolet spectroscopy to sum up, and the quantum physics came in to rescue that. But unfortunately, it also fell into a problem with general relativity in the sense of vacuum spectroscopy, where you have the worst prediction of the vacuum energy uh, with respect to the observed phenomena. So we realized the importance of the physics the, of coming up with theories, but it has to be confirmed by experiments or observations, things like that. It's very important. So that's what we are trying to do. So the quantum and relativity again made people to really doubt about the very physics itself, and the faith on physics itself was at stake. But we want to revive. I mean, still a lot of good things about physics, very important for us. We cannot abandon physics. So the quantum physics and the general relativity somehow to come together and see how they can patch up that. So there are various attempts, and that's one of the things we will go through. What happens? So in this episode, we are seeing how to retrofit quantum and relativity physics to come up with the grand unifying theory. This is the idea of theory of everything. So what are the things? So we are not going to too much mathematical details or anything or philosophical aspects, but historical aspects in the sense that how it progressed, how the progression occurred. So we start with the first with the historical perspectives, quantum relativity. The quantum mechanics, as we know, the 20th century, Max Planck, they were the great scientists, Albert Einstein, Niels Bohr, and Schrodinger, revolutionary understanding of the microscopic world. We knew that the microscopic world is important because after coming up with the idea of radiation, that eventually Rutherford said there is, the particles inside, charged particles like electrons and protons and all, is very much part of the what we see from outside the mesoscopic level. So the Planck introduced the concept of quantized energy levels, and we know that the radiation is not occurring continuously. It's not a continuous spectrum, but actually it absorbs certain amount of energy because before it releases that energy in the thing. So that's what quantization is. The Morse model explained atomic spectra. So the atomic spectra that we saw, uh, that we understand about the material, it becomes the main aspect, right? X-ray, diffraction, and different aspects. RJ spectroscopy. The spectroscopy has become the most important aspect to understand what's going on inside the material. The Schrodinger wave equation provide a mathematical framework for quantum mechanics. So that that introduced the quaternions away from the scalar or real things, but imaginary things. The wave equation included imaginary term in Schrodinger equation. That was the main difference. But relativity theory came around the same time. 1905, Einstein came up with the idea that space-time and energy, and he said that entirely the gravity is not a Newtonian thing, that actually a curvature of space-time is what is creating gravity. And in the special theory, he said the speed of light is constant, regardless of the observers, and Lorentz transforms and things like that are important things. And he said that the mass and energy are equivalence, E equal to mc squared at the microscopic level, the quantum level, what we call it. Uh, so general relativity described gravity as curvature of space-time due to massive objects. Quantum field theory then came up to bring together quantum mechanics, special relativity, and then electromagnetism, weak force, strong force are seen to be interactions between fields and particles. So essentially, everything is in terms of fields and particles. Uh, is the description. So the unified theory, and we went through some of the details in our previous episodes. I'm going to repeat all of that details, but essentially, unification involves a reconciliation of quantum mechanics and relativity in term to come up with a theory of everything. That even the famous Stephen Hawking and everybody started on and still going on. So the quantum gravity is one of the main aspects in this, uh, because the uh, the other aspect, which is mathematical, is the string theory and loop quantum gravity. Uh, is the one that is trying to come up with a comprehensive quantitative means of understanding everything. Uh, in this situation, the black holes become very important part because as we saw the Schwarzschild metrics, which eventually predicted about the black holes, and somehow it has been experimentally seen, but there are controversies surrounding that. But the quantum effects are very important, and Hawking said about the quantum fluctuations and the Hawking radiation, things like that, about the event horizon. So black hole physics is a whole new physics that's going on. Then we have the measurements in terms of cosmic microwave background that we get the radiation, which tells us what's happening in the early part of the universe, how the universe developed. And there are a lot of questions about that, but they support quantum and relativistic predictions in many ways. Then we have the quantum entanglement in space-time, entangled particles. The quantum mechanics predict about the entanglement aspect. Uh, they violate classical locality, as we know, Bell's theorem and all that. Uh, and then it challenges space-time notions. So the whole thing comes to an emergent space-time aspect. Uh, so the whole idea of space-time emerging from underlining quantum structures is very much in the vogue. Uh, The practical application include now the quantum computing aspect, which is revolutionizing the whole area of technology, along with the AI, the artificial intelligence. They exploit the uh, the main principles of quantum mechanics, like superposition and entanglement, uh, to create faster calculation processing of data. The GPS and relativity very important. We depend on GPS for most of our uh, transportation, for our navigation systems. They layer accounting for relativity effects due to uh, its gravity and motion. And the uh, quantum sensors such as atomic clocks. They keep the time very accurate to the minute second. And magnetometers enhance precision navigation, because in navigation that's very very important to keep track of the minute aspects of time, communication, scientific measurements. Uh, so we go into the space-time general group. In terms of understanding, pulling back a little bit, historical terms instead of geography. So the physics has to somehow connect with the rest of the world, right? The geography and everything. The composition in historiography uh, revision is just a little bit off track, but it kind of sells a story, a challenge dominant narrative. The stories engage with the spatio-temporal dimensions, emphasizing space and time intersect. So, how did the space and time aspect came to be? So, when philosophically, and NASA, the last 50 years, space flight exploration scientific endeavors also involved with sending out telescopes like various types of Planck telescope, James Webb, Einstein, different Chandra telescope. They all look at the universe and try to figure out, what was happening, so that we get signals from them and analyze them and understand what's going on, really in the astrophysical level. Uh, so, and this goes back to the idea of ancient Greek philosophical. Early Greek thought about the boundaries between space, time, and matter. Uh, so it is not distinguished from temporal or time aspect. So Plato's timeless gives the concept of time and space independent magnitudes. Uh, but the how they affect the motion and change was really not clear at that time. So Aristotle came along and said that time and space are distinct and unable to address Zeno's paradox. So Zeno's paradox is very important because it says that the motion itself is not really real, but it's illusion, and it supports Parmenides' doctrine of monism, that all reality is one, all change is impossible, nothing ever changes in location or any other aspect. So it's a very, very extreme level of understanding the motion is just we perceive in our mind. And working with Emery Taylor, there is some aspect of reality that we are coming up with, what our mind sees versus what really is, things like that. But the ancient timekeeping, and I research with, also with Christopher, Emmanuel, all bring out these aspects, even Christian and all our group, John and David Reading. Uh, we have very similar views, but also we have our own models that come up with that. But the timekeeping is important. We cannot totally deny the aspect of time. The time itself may be illusion, maybe a create construction of the mind, but it is something that we follow, thoroughly. Uh, and that's because the celestial events and the activities are based on the rising and setting of sun, solstices, lunar phases, star positions. Uh, they are all worked through a cyclic aspects and a clockwork kind of thing. So we cannot deny that aspect. So archaeoastronomy suggests that astronomical knowledge shape people's concepts of space and time. So celestial patterns very very important for people, even for astrologers. Uh, the global perspective, Greece, Babylonian, Egyptian, Chinese, Indian, and American societies, there are unique systems for understanding the heavens, what we call the heavens. So, in terms of quantum and relativity, the quantum gravity and determinism became the important aspect that started developing. The early 20th century, quantum theory challenged classical physics, like I mentioned earlier, and previous episodes also brought out this aspect. The quantum universe actually may be more deterministic, surprisingly, classical one. That's something that we may consider as we go along. The physicist James Hartle proposed a remarkable idea of quantum gravity to unify quantum mechanics and relativity and to restore determinism. Uh, to explain why the universe is like it is rather than some other vision. So we take it as it is condition of the universe. The emergent properties that come up with our Stephen Wolfram and collaborators, relativity in space-time curvature emerge properties in certain universes. So relativity talk about space-time curvature in one universe, but the quantum mechanics emerges studying universes differently. So it's a perspective that we see uh, that challenges the traditional dichotomy between the quantum mechanics and relativity. They are actually intertwined aspects of a deeper reality. But that deeper reality is something we still have to figure out. Holy grail of physics then is the finding a TOE or theory of everything, uniting fundamental theories. While the quantum mechanics govern the micro world, the relativity in general talks about large scale evolution of the universe, what we call the astrophysics aspect. Achieving this synthesis will revolutionize understanding to bridge the gap between quantum and cosmic scales. The emergent property, for example, consciousness, and people, scientists are now talking, physicists like Penrose, talking about consciousness itself, what it is, and Sabine Hossenfield, people like that. Uh, phase transitions, how the phase is transitioning. Like I talked with Emmanuel about the phases, that superluminous phase, how everything came from superluminous condensate. Self-organization. Uh, that's something that is how the world eventually is doing naturally. It's doing self-organization aspect. That's a very important thing that we have to understand. uh, Superconductivity, magnetism, life, economic system, social phenomena, and saying that the whole can be greater than the sum of the parts, things like that. So these kind of philosophical aspect is coming. And you know I also think that besides this point, which will come up later about the matrix simulation program, things like that could be happening. Uh, that could explain some of the self-organization aspects, but we'll see. But essentially, string theory overview. So the string theory became one of the most beautiful mathematical theories of the modern physics. They propose fundamental building blocks of nature, not point like. So that's the idea from after Rutherford, there will be that the electron is a point particle. But and the question of mass, especially for photons, is still a big question. It's a massless particle thing. But string theory goes away from it and considers everything as one-dimensional strings that vibrate in a higher dimensional space. So it's developed many dimensions in that sense. They oscillate at these strings oscillate different frequencies, very similar to musical notes. So it is connected to the music, like if you have a guitar or violin, everything. How these strings, vibrate, and the particles are very similar, like photons, gravitons, quarks behave similar way. They It offers a unique perspective of the fundamental nature of reality. No question about that. So, how to unify the quantum mechanics and the relativity? Uh, Quantum mechanics essentially concentrates on the understanding of particles and fields on a small level, whereas general relativity talks about the gravity and space-time curvature. But when they clash, they create paradoxes, such as we know about vacuum catastrophe, things like that, and inconsistencies. The string theory attempts to bridge the gap by incorporating principles from both of the quantum mechanics and general relativity, but it comes with extra dimensions, more than the three spatial dimensions and one time dimension. Mathematical complexity challenges. String theory complexity poses challenges, but it has not been proved experimentally. And that's a big problem in physics because without experimental proofs, we cannot fully accept any theories that is although it's maybe most beautiful mathematical theory. The vibration modes of theory give rise to rich spectrum particles, including graviton, which is being analyzed, including my manual and other associates that we have doing that. And myself, Christopher, others also consider deeply about these aspects. Experimental verification remains difficult due to high energy levels, but like a larger hadron collider, things like that, is one of the ways we can figure out these particles, but these require much higher energy than possible right now. So the researchers still continuing to come up with a, empirical validated string theory that's still up there. Uh, and I want to tell you many of the references for these I will put at the end, the whole list of references uh, from which I got this literature review. And you can go in more detail. They go into more detail about mathematics and the physics, and that's very, very intriguing. So the standard model, of course, became the main aspect with quantum gravity, quantum mechanics. As we know about the weak theory, which was proved very well, the Abdul Salam theory, electroweak theories, which was fundamental basis for quantum gravity. And later on, Higgs mechanism, things like that came into being. But I also talk about Newtonian modified physics. So we start with the quantum gravity and the standard model. Uh, so the general relativity, as you know, is about gravity, and then quantum mechanics is about particle behavior. Uh, the local excitation can be mapped to the first general fermions. So the standard model considered fermions instead of just electrons, and they classify all the electrons, all the spin based on the spin of the particles, half spin particles, as fermions in general. So these states propagate coherently, behaving noiseless substitution microscopic quantum mechanics. So how the signals come into being is being really pursued. The Prion model, which is the subcomponents of quarks and leptons. As we know, there are there are subparticles. There are particles which are very very their lifetime is extremely small and they are not real particles. And the Prion model came into being to understand that quantum gravitational foundations. So in this case, the matter seems to be inherently included in the microscopic kinematics and dynamics. That's very important because the mass of the particles, the real matter, is always where is it hiding? That's the whole question. The Newtonian quantum gravity, on the other hand, is essentially a nonlinear quantum theory of Newtonian gravity, which is consistent with objective interpretation of the wave function. So that is another area that's developing. The Schrodinger and Bell, uh, you know, aspects help to map complex wave functions to configuration space to observable fields in space time. So this is being developed. So how gravity might manifest quantum level while adhering to the principles of quantum mechanics is a big aspect. The modified gravity, recent report says that there is a aspect that shows that there is a breakdown of standard gravity law acceleration limit. So the Newtonian gravity may not hold good the way it was classically presented. So orbital motions of binary stars, for example, reveal deviation from classical gravity. The challenge ongoing Newton-Einstein theory hindered need for modified gravitational models. So we have to keep moving. And now comes the idea of symmetry, the special symmetry group and particle field theory. Uh, so the symmetry provides essential constraints And we know Noether's theorem is the fundamental thing that talks about conservation laws, deep connection between symmetry and physical quantities. Uh, the Noether's theorem states that for every continuous symmetry in a physical system, there exists a corresponding conservation law. So that's a very, very deep thing that may be the most fundamental aspect of all of physics. It guides the formulation of Lagrangians by ensuring that desired conservation laws part of the theory and with invariance based on observed symmetries. So this is very, very important that how the invariant conservation symmetries hold the most important part. And we know that that's the holy grail of physics, the conservation laws. Without that, there may not be any physics. So understanding symmetries helps predict system behavior and provides insights into eigenstates, which are the quantum essence of the quantum mechanics. Okay. So the continuous symmetries and conservation laws. Continuous symmetry like translation, rotation, grooves correspond to so in terms of the movement, microscopic movement of atoms or things, how the translations, rotation, how they how they conserve the quantities of energy, momentum, angular momentum is a fundamental criteria to understand. For example, quantum operators associate symmetries reveal fundamental properties of physical systems. So can we really quantify the properties? I mean, qualify and quantify these properties. So now for that we have something called SU2 symmetry group, the special symmetry group, and the spin aspect. The spin matrices represent angular momentum components. Very important. Pauli and Dirac and a few other people have come up with the idea uh, how the symmetry and the spin comes to be. So irreducible representation of SU2 describe different spin states. As we know, that's how the classification of fermions, bosons, and gravitons, things like that, based on the spin aspect that we talked about earlier, and we'll be talking about further speech source, little more details about that. So spin n particles representation of c to the power of 2n plus 1. So the permutation combination become important in these cases to describe them, the actual. So like there comes the Lie groups and Lie algebra. So SU2 is a compact Lie group of unitary 2 by 2s. Talks about supersymmetry, things like that. Complex matrices with determinant one. So unitarization is very important aspect uh, to take care of the units and other aspects. The Lie algebra, the small SU2 corresponds to infinitesimal generators, capital SU2, forms the basis for spin representation. So that's all new algebra, the algebra of SU2. Application beyond. Symmetry concepts extend to quantum field theory, very important part of the quantum field theory. Without understanding this symmetry, SU2, SU3, U1, and all, it's impossible to understand quantum field theory. Standard model contains matter physics as well. Uh, so irreducible representation is the main thing that give insight to quantum spins and other physical phenomena. All right. So special unitary group, invariant, gauge transformation, general lattice. So again, we are putting together all of them. The lattice gauge theory is the next advancement. Uh, so gauge theory again, talk about Maxwell equation. The gauge fields are, again invariants under different transformations, uh, and that helps to develop a quantum chromodynamics, QCD, on discretized space and lattice. So believe that there is a lattice underlining uh, finite dimension lattice to find the path integrals like the Monte Carlo simulations. So the lattice geometry part is very important for the structure. So there may be a super lattice, for example, which are nice arrangement of whatever the particles are in a certain specific pattern, much like our uh, materials aspect crystals. The continual limit, uh, the infinitely large lattice with infinitesimal spacing will recover original gauge theory. So the gauge theory can be, can be conserved and also uh, be reconciled with this idea of lattice. So SUN representation, lattice gauge theory, there's something called Wick rotation based on the quaternions, and that can be transformed into Euclidean space, which then does the uh, conform to the lattice aspect. We do a lot on that, transforming like very similar to what we do in diffraction methods, uh, that we find the lattice constant, things like that for crystals. So very important aspect. So SUN gauge theory, we assign SUN matrix, which is part of the Lie group, connecting the lattice sites. So very detailed aspect. Uh, the fermion fields, in this case, the fermion fields, like the electrons, they reside lattice sites, while gauge fields live on the links. The link, the one that links them, is the gauge field. So it's very nice theory in that sense. Uh, how the particles and the fields come together, the fields and the quanta that the many scientists talk about are very important part of that. The loop and string operators. So canonical transformations are, essentially canonical means you can talk about momentum based or position based aspect. We can transform them like legendary transform, things like that. So the canonical transform reformulate SUN lattice gauge theory using fundamental loop and string flux operators. So these are details that go into that. And something called Wilson loops and packets, uh, which are like circuits of the lattice rotation, and the strings and flux tubes in the lattice. So the actual flow and the current and the pathways, the trajectories, everything are very accurately described by these uh, concepts. So because of the SUN Gauss laws, SUN string degrees of freedom become cyclic and decoupled from the physical Hilbert space. So that's something that has to be considered. So these are the intricate details that happens with that. To go into details about the materials and the environment aspects. So the Hamiltonian invariance, the Corgot Susskind Hamiltonian, to describe the fundamental operators exhibits global SUN invariance. The invariance, like mentioned earlier, is a very important property. So in this case, there are no gauge fields. So that simplifies the dynamics. Considering gauge fields always is difficult, because of the complexities involved. We have to even go more complex than the Maxwell equations. Uh, so they're trying to find a way out of that. The continuum limit, the weak coupling effect, lattice spacing approaching zero, the SUN loop dynamics resemble SUN spin Hamiltonian with nearest neighbor interaction. So these are the intricate details which might solve the problem of how the gravity get incorporated into the quantum mechanics itself. Okay. So so then so that's essentially what it is. I don't want to go into more details than that right now. Oh, what happened to the, let's see. Hopefully it didn't go
Oh,
off.
that's great. Thank you.
Yeah, is it okay? Thank you. Now, I just want to give a little bit and also references. That's it. Another couple of minutes, few minutes. So
Sure,
upcoming
sure. Yeah, go ahead.
YouTube. Yeah. So one of the questions. I mean, just a thought uh, that the energy in general may get into two parts. In quantum physics, in space and time, as we know, we can separate space and time. And I work on the time aspect, for example, and Christopher works on the space aspect very nice separately, and then we'll try to put them together. Generally, it's electromagnetic on one side and gravity on the other side. So these are the energy getting divided, and something that we'll keep in mind as we go along and go along the episodes. And once you finish that, we'll come to our current state of affairs. The episode, just want to put a heads up. 7 to 10 will continue analyzing new particle field theory, quantum gravity, supersymmetry, M theory, which I'm going to say why M theory, why we right now, I think even loop quantum gravity has been falsified to some degree. So we may have to go up to M theory. That's the present understanding. We'll see. So gauge theory, brains. So M theory is very closely related to brains and gauge theory and all come to be. And hopefully that will go into theory of everything. And then in terms of the references, you have the 5 problems in quantum gravity, astronomy. So we have different references here, all kinds, but different field, but time and space, ancient times, what happened with Aristotle and all. What is happening with the theory of everything. So people have written about that, a very detailed aspect. String theory, these go into details about the math aspects, quantum gravity standard model, Newtonian quantum gravity. Uh, then we have the quantum mechanics statistics, bootstrapping Newtonian quantum gravity, Lie groups, introduction to quantum spin aspects, the symmetries, the flavors that talks about the strong theories, uh, the Gell-Mann aspect, the matrices, things like that, symmetry fundamentalism, field theory, standard model, canonical transformations, generalized global symmetries, symmetry conservation laws, lattice gauge equivalent that I talked about briefly, external imaginary gauge transformation, Gell-Mann matrix, quantum simulation, pre-potential formulation, SU3 lattice important for the quantum field theory, and also the strong field. The loop strong string hadron formulation, the aerodynamics, which is becoming important now. People are looking into that more detail, and gauge theory that he has extensive, like more than 400 pages. Tong, who is a professor of in Cambridge, one of the top professors in Cambridge University, and he talks about the entire aspect, lot on monopoles, things like that, which we like. He emphasizes how that comes very detailed analysis, complete math uh, towards TF everything. So these are the main things. Thank you very much. So essentially that essentially concludes my uh, presentation, and then open for discussion. Thank you. Right now, I don't know whether should I keep that on or not.
I don't know if you feel like you need to reference it or something, you might. But
I'll keep it on.
it's up to
Okay.
you.
Okay.
Okay, yeah, fair enough.
Yeah, I
So
keep it
yeah,
on.
good presentation. Interesting topic
Thank
on
you.
string theory. We've come a
Thank you
long
very
way
much.
since the
Sure.
beginnings with Faraday and
Yes.
Newton there into the more
Yes.
modern era, which
Yes.
is interesting because I mean the foundations are good to know, aren't they? But
Yes.
sort of when you start getting up to more up to date contemporary stuff, it becomes a bit more relevant and exciting and on the frontier of what can be discovered and known about. So
Yes.
that's what we're all into. So sometimes we have to go back into the past as well to sort of recapitulate and also to just understand what it was they were trying to say, because you know
Yes.
it's a deep sort of subject, so that you can spend a lot of
Yes.
time on. So one thing that I noticed you mentioned that I'm curious about is this issue about loop quantum gravity.
Yeah.
I think recently did they say that it might have been disproven?
Yeah.
Hmm.
Yeah. Now
Any
I
more
saw a
info on
paper.
that?
Yeah, there's a paper. I forgot now. I should have saved that. I forgot the. I saw it when I was in India, for example. I saw this paper. I may
Yeah,
have it in my email. I have to dig it out. But
yeah.
I
I think
looked through.
Emmanuel sent it on. Did well? I think it was a
Yeah,
video.
yeah, probably,
It was a
probably.
YouTube
I think
video.
Emmanuel. Yeah, I think so.
Hmm.
Yeah.
But I didn't get a
Which.
chance to read the paper or anything,
Yeah,
or
yeah,
even look it up. But that's a good idea. I might have to
yeah,
go and
yeah,
do that because I mean, obviously. So, what's your what are your thoughts on loop
yeah,
quantum gravity. Do you have any, or have you
yeah, yeah,
looked into it at all?
yeah. Yeah, I went through that some of the I have the extensive. I wouldn't say extensive, but some the references I gave, like 3 page. So in that way, loop gravity and went through that briefly. I didn't have chance to peruse the intricate math, but I did go through
Yeah,
them loop gravity and
yeah,
if I remember, that was like few weeks ago. I actually went through them in some detail, to understand them. There's a lot of math
yeah.
involved, um, but in the loop gravity, essentially, what is happening is that I also believe partly that that it creates somehow the vortex fields. The understanding of vortex fields, I think, to understand the math of the vortex fields is,
Hmm,
I think they are bringing back because originally Maxwell also thought about this vortex aspect, but he kind of
hmm,
went away from it. Uh, so what's creating that vortex? They are looking into that the lattice, uh, what is happening at the local level, the fields, how they are, how they are emerging. So they talk about the fact that you need a certain amount of level of the SU2 group. So they are going from so they go SU4 and go up the ladder, and each of them they're
oh,
analyzing the loop gravity and
oh,
seeing is that gravity created by a loop of the fields, how the fields are looping around, because you have interaction between electric and magnetic fields and how they're, that's the intricate math which is based on the group theory. It's very, very complex math. Talks about the
yeah.
chiral aspects of the
Hmm,
groups itself. I think you are considered aspects of the chiral aspects
yes.
in the group theory. You are analyzed from a different point of view, but they are
Yeah.
looking at from another point of view. And if I it's so complex, it's so mathematically so complex that I'm trying to
Hmm.
see what is I was trying to see what is I had to go back again to see what is the underlying principle. And there's one person, I don't know whether I have put that reference correctly, but I went through his thing and he seemed to be he's a Spanish guy, I think, but he seems to have done fairly good job of explaining. But he does go into, I don't know, it's Alvarez or somebody like that. I'm not sure,
Oh, I've heard
but
that
I have to
name. Yeah.
see. He may be one person that he talks about that. But the loop quantum gravity, let me see, loop string hadron formulation. These people I went through yesterday briefly, and they seem to explain some other things. But
Well, hang
unfortunately,
on.
they start.
A loop string sounds very like string theory, doesn't it?
Yeah, they have lot to do with string theory as well. Yes, that's correct. And
Oh,
then the quantum
I thought it
simulation.
was a
Yeah,
contender to
yeah,
string theory. I thought it was being made out as like a contender to string theory. You know, that it was its own thing.
yeah, yeah. So
Because
yeah, there's
in
lot.
this week it
Yeah,
was news came out that it had been disproven, and it was like
yeah,
string theory was somehow put back on the map because of this. Although I don't really see how that works. I
yeah,
suppose they're just the last, maybe the last ones still standing. You know, maybe that's what they
yeah.
mean.
M theory.
So,
I think the next one. Now I like the M
mm.
theory. That's the next one. The M theory with
Oh, is
brain.
that the
So
next
I actually
episode
I
you're going to
have
do?
later on I will present that.
Mm.
Yeah, I'm going to. So I know that we have to go into brains, and even I talked with Emery about that. You may see one of the earlier discussions where Emery was there. I think a couple
Yeah,
of weeks ago. That's also in our live broadcast. One of the episode, one of the not the episode, but one of the discussion where Emery and myself were discussing a lot of things. That was
yeah, I saw
extensive
that.
discussion.
That was very
Yeah,
interesting. I like that. I hope
yeah.
that
So they
Emery
are.
comes back and we can continue that
Yeah,
conversation, because
yeah.
I think I have a few
But
things
yeah,
to
yeah,
I have a few things to add
yeah.
on onto what you guys were saying. So.
Yeah. So
interesting
one
conversation.
hour simple. Yeah. To put simply, the brains, the distance between brains is the discontinuum length. That's one of the things we have come up with. And I am like you helped me a lot, Christopher. Thank you for putting the Python thing, so I can use that program. And I have to still work. It's like try and error method, but at least I know what to
Of
do
course.
to
Yeah.
create that discontinuum science model wave. So I have come up with something that's coming up. I am adjusting the parameters inside inside the Python, because now I can run the Python thanks to you, and it's working well. But I had to manipulate the code to get what we want, the output we want. So that is a lot of work. But I think but at least we know what to do. So then we get a discontinuum thing. The uh, discontinuum length is constant. So that is the important thing. So the distance between the brains, the flat brains, I call them now flat brains versus curved brains. Now, flat brains are like vacuum. In vacuum, they are flat brains. So they are the equidistance. That may be one of the reasons the speed of light is constant, for example. So that's something calculation we have to make, very deep ones. That's a very deep theory. Then the time itself, as you know, I said it's a tensor. So what is happening in the future? It is the time is developing so many scenarios, right? Many different wave functions, and then so these are tensors, so they're not scalar. We cannot measure them. So that's why we cannot see the future per se, but it's already developing some many different many words, many things, many possibilities, and then it collapse to one possibility. So that's how the scalar time moves on, the event moves on, and then it becomes the present. So that's how it is developing. So in that situation, the time affects the brains, and it curves the brains, much like we call the gradient and everything. So you have curved brains, and these curved brains combined with the flat brains create curled up dimensions. This is my present understanding. And I come up with the understanding of spectra, because what is the essential information that we get from outer space? Just the signals, right? So I came up with the idea that how do you plot the signals, signal to noise ratio, in terms of a coordinate? So I start with a very fundamental absolute thing that I get some signals, and these signals, I described signal to noise ratio. And my model says that the whole thing, superluminal thing, is a noisy thing. So it's a infinite. The signal to noise ratio will be zero. But what is happening is that as we random fluctuations, it creates activated, distorted field locally. So that noise is called activated noise. That's finite. So now the signal to noise ratio is not zero. It's something greater than zero. So we start seeing the signal coming up, and then so it converts to signal and that aspect. So that signal
Well, how
is,
do you, let's say you have a non-zero signal to noise
yeah, yeah,
ratio number, right? But how does,
yeah,
so let's say
yeah,
you've got that number, and I don't know, it's an integer, it's the number three. How does that
yeah,
help you find the signal, or does it? Does it just indicate that one is there? Is that the
yeah,
idea? Ah,
yeah. So this is a
okay.
very
Can you
fundamental absolute
elaborate
thing.
any more
But
on that?
yeah, actually, I don't know whether I can show you. Let me pull out that. Maybe that will help a little bit. Let me try to show. It's very, very intriguing, very, very nice. Uh, so I want to show that if it's possible. Let me see whether I can pull up that 1 minute. Uh, it's a very recent thing that eventually I think I will publish that. But I mean, this has copyright, so I'm not too worried about that, because what I present here as copyright. So let me see. Okay. Okay. How do we get and how you can see that?
Oh no, I can't. You're gonna have to stop
Yeah.
sharing your screen. Hello?
Okay.
Yeah, and
So
then
now
if you
you
can,
know.
if you could make that a solo layout, um, you click the three little dots in the corner, I think, or maybe at the bottom of the screen you can present that like
Oh,
solo, so it becomes, yeah, that's it.
okay. So if I can, in a way, I'm trying to see without getting shadows. So this is a signal
Yeah.
spectra. Uh, I actually
Okay.
are not showing the most fundamental thing is just a signal, and this is some coordinate. But now I find that coordinate is space and time. Okay, so it's the next
Right.
level. I'm not showing the most uh, rarefied thing, but it's some signal. You get. This is what we get normally, and actually you can show that that's the case. So I say IJK things which are crystallographic directions, which is very similar to lattice things. And
Yeah.
the J variable is the I variable is the time. But this time, I show that this time actually is not a linear thing. It's a quaternion. So when we differentiate, we have to do a differential uh, instead space and time. So this is a differential of del of nm, where n is the dimension of the space, so x to the power n, and tm is kind of a virtual dimension of the time. As we know, time is a tensor according to me. So when we do that, we get power density spectra, and this power density can be connected to temperature actually. So when I put them together to go, this is a little bit detailed. I have to work it out to publish, but I this is Emery's thing that you have discontinuous signals. So they are DL. So there is a gap in between. This gap is a continuum thing. And if I combine that together with the signal that I get from here, I get these spikes, spikes in that sinusoidal thing. So I can use algorithm. I come up with the algorithm. Now I have to manipulate the program. So I have the uh, Fourier discrete Fourier algorithm, and then I have to formulate this one. I know whether you can see that. I have to formulate this one into algorithm. So when I do that, I should be able to simulate these graphics, by manipulating the codes. So that's the next step. That may take a while. It may not be very
Okay.
easy, but
But how does
then
that
I
how
should
does
be
that
able.
answer my question? So the other question I have, which is kind of related, would be
Uh,
so what equation are you using to determine the signal to noise ratio? Do you take
ah,
the peak?
good question.
Do you take
So
the peak of the signal minus the?
yeah, so one of the things I have. Okay, my original equation is uh, signal is a
Or
is
divide it.
a
I guess it's
function of
divided
noise.
by.
Yeah. Then I divide by noise. But I had to use noise because if I use the large noise, I get zero. So it's infinite. But this is not, it's finite. It's activated noise. So this is a gamma.
Okay, but how do you get the noise? How do you
Yeah. So
what's
it
the
may it
method
may
for it? No.
yeah. I have, for example, I have very simple physics is that this is a translation wave and this is the vortex, right? I have equation for that. So this is the noise. So I can calculate this one from that. It's a little bit math involved, but from that math, which I have developed from the 2 by 2 matrix, things like that, you can actually get the connection. I had done in some previous uh, uh, peer published papers. So I'll pull out that, and I have
Yeah.
connected the signal to noise ratio to uh, the actual fields and the wave functions. So from there, what the possibilities of wave functions are, you can actually calculate the signal to noise ratio.
So
You get an
I assume
algebraic
that
equation.
the wave functions are the signal or something.
Yeah, yeah. These are, you can convert them to wave functions and also the
Hmm.
gauge field. So you have the inner
Okay.
product, outer product, and all that, right?
What's
You
so?
can the
Hmm.
density matrix, things like that, and the
Yeah.
what you call the dot product and the cross product, the inner product and outer product of the gauge field and the wave function. So using all that,
Makes
you can
the
come up.
that gives you what the probability distribution.
Yes, and from there you find the energy because the signal to noise
Okay.
ratio is directly to the energy because it shows the energy content, right? So
What
you
is the
these are unit.
what does the cross product give you? If the dot product of the
Yeah,
wave with the with the
a gauge
something.
field, gauge field, yeah, the
The
field.
what does the inner product give you?
The inner product gives you the density matrix,
The
how it
density
is,
of what?
the density
The
of the
density of
signal,
what?
like the signals, like you have the signal gamma 1, gamma 2, different signal to noise ratio.
Oh,
So if you,
so is
yeah,
this
so
so this is kind of
how it
related
is,
to your. Is this like something that is done a lot with Schrodinger waves and all that, or is this
yeah,
something
it is
more?
it is connected. It is a little more
Okay,
advanced than Schrodinger thing. It's the next level of Schrodinger. You have to go
okay, but
further than
it's like
Schrodinger.
this is sort of would this be standard physics that you could find in the textbook, or not in textbooks, but in
It's derived from that.
journals, papers?
Derived from that. They are not there. What I am saying is not there, but it's derived from that
Oh,
because everything refers
interesting.
to
So,
inner product,
what is the
Schrodinger
what
equation.
is the
Yeah,
logic behind? Well, when you get the right, so the dot product gives you the probability distribution, and then
yeah.
the inner product gives you the density. So
Density.
how do you,
Yeah,
yeah, how do you determine that? I'm kind of curious about, you know,
yeah.
what is the logic behind the
The density.
that
Yeah.
to find, yeah, because wouldn't density be like the number of particles over the volume or
Yeah.
something? And
Eventually.
right,
So
and what is the
what
dot?
is
What is the dot product tells you? Um, I don't know, is it the cosine distance or something like that? But it's a and then the inner product is defined as what? It gives you back a scalar number, doesn't it? Something.
yes. So
Or,
inner
or
product
is it a pseudo?
actually
Does it give? No, wait a second. The dot product gives you a number. The
yes,
inner product gives you like a pseudo matrix or something.
vector. Vector. Yeah, it's a vector. You get some vectors.
Right.
So these are vectors, but you can
Okay.
scalarize
So
them.
how do you have a vector density matrix then? What is that? Oh, it's
Yeah,
supposed
it's a
to
vector
just
density.
oh,
You can
interesting.
scalarize them. You can scalarize
So
them.
is that
You can
does that
scalarize.
become like a Lagrangian kind of, or if it's
Huh?
if it's a matrix with a density, it's a tensor, is it?
Yes. Yes. So it's a tensor, but you can
Oh,
reduce the rank of the tensor. There is a way to reduce the rank of the tensor and finally
oh,
scalarize them. This is what I'm doing in one of my current ongoing. I think they have accepted that it should be coming. I should be getting Galley proof. I talk about how to reduce the rank of the tensor grade. It's called gradation, and then match the ranks, and finally get into rank one, which is a vector, and then the rank one, rank one is like, your speed or, your velocity, that kind of thing, momentum. They're all rank one. You can describe in terms of rank one. And then how do you scalarize them? You have to scalarize them to make it measurable, observables, right? Measurable, like speed. Speed, you have to convert velocity into speed. Uh, that's scalarization of velocity into speed, which is speed is a scalar, so we can measure them actually. Uh, so those are the processes I'm going through, but I think there is a method to do that. So very, very carefully you do that. You don't make mistake in that. So, there is no assumption. Ensure that there is no assumption, but only a just a mathematical transformation. So I'm trying to see, you know, without introducing any assumption, how to do mathematically, and that's what I'm going through. So, but this density matrix will give us how it distributed. Like they are almost like particles, like charges, and connect with charges and mass and charges, right? Like if you know charge and the mass, E or M, we know what particle it is electron or whatever it is. That's a fundamental thing. Now we talk about spins, a little more complex. How the spins are the spins half or one or more than one, things like that. So we now know what particles they are. They're fermions or bosons. So these are the next steps, bosons or gravitons, things like that. So it could be all distributed. So depending on this, we convert that. We convert that based on where is it? Let me see it. Sure. Yeah, we convert this density matrix uh, in terms of charges and mass and spins. Then we can know, okay, is this a electron or fermion, or is this a boson? How it's distributed? How this particle are distributed? So distribution of particles we can figure out. So the spectra of particles, are they mesons or are they hadrons or fermions? All this we can figure out. And based on that, we know, are we talking about strong forces, weak forces, electromagnetic or gravity? I believe fundamentally, right now, from the brains, you can say there are only two waves that comes out from the brains. One of them is the cosmic microwave background, the flat brains, and the gravitational wave for the curved brains, which talks about the gravity. So these are the measurables. So you have to connect that measurables. We have to connect our theory finally. So theory has to be developed such perfect level, hopefully, that it will connect to the cosmic microwave background, which we can measure, the gravitational wave, which we are able to measure. These are the two main things we are able to measure. So connect to that and the theory, and then say, okay, how the curved brains form, how the flat brains form, and so these kinds of things start coming up. So this spectra we can connect with. Okay, most likely this spectra is connected with cosmic microwave. The spike is connected to probably gravitational wave. So we individually go point by point and see how the spectra is changing. And then we can interpret the spectra in terms of the vibrations or light and sound, so to say, or the vibrations versus the radiation. You know, so this is the ultimate goal. Ultimate goal, but we are a lot to go. But I think
Yeah, where
halfway
are you
through.
getting the spectra from?
Huh?
Where do you get the spectra? Oh, it's from the yeah, okay, the superluminal
Yeah,
aspect.
yeah, yeah.
Okay,
Remember,
okay,
I had that model. I had the schematics. It shows how you can get these things from the superluminal thing, from the noise. You know, the locally distorted field. It creates a locally distorted field, and you have the hot PDP mechanism operating there that creates these kind of particles. So you know, so hot PDP mechanisms aren't particle, right? Like they're not particles, but by the mechanism operating, they can create these particles. And you have question of a false vacuum. Another thing that is coming up in the chapter is in a book that should also come up this year sometime, is how the false vacuum could be like a crucible for the hadrons, the strong nuclear particles, and the true vacuum could be for fermions, you because false vacuum higher potential. So those things, but the math has to work out. So again, that's a lot. I'm trying to reduce the amount of math. I think the math creates a lot of additional problems. So I'm trying to reduce the amount of math and use applied math just enough to describe the physics, but also it should be rigorous enough. Uh,
Yeah,
just a minimal math, I'll call
that's
it
a
a
really good
minimal math.
idea. Yeah,
Yeah,
because
because I
that's
don't
the
like,
problem. It's a lot of this
yeah,
maths that I'm looking at. It's very like you were saying in your talk actually about
yeah,
well,
yeah,
the sort of the rectification of initial conditions through the Lagrangians or any
yes,
Noether's work
yeah,
on
yeah,
conservation laws.
yeah,
And then they have
yeah,
these, so we have these complicated sort of group transformations, and then you
yes,
want to sort of apply the Lagrangians to those, and then the
yes,
equations just start to look very daunting, don't they? And
yeah,
so you're
yeah, yeah,
saying they want to get rid of that, is it?
yeah, yeah. So that's why I use something good. I think the problem is they are tied up with tensors. They are not reducing the rank of the tensor. So you need first to reduce a way to reduce the rank of the tensor by gradation. You are not just, brute force. You are not doing that because that will not help you. You have to
Yeah.
do a proper gradation of the tensors. So you have like rank six tensor, or you have to convert to rank one, which is a vector, and the vector is more
Mm.
manageable because we know many other quantities are vector, momentum, force. As we think, force is not really a vector, but the speed, the velocity is a vector.
Hmm.
Momentum is a vector. Momentum is a vector. You can say because everything, you can measure that. You can actually measure these quantities, but when you measure it, it's scalar. So you from vector, you have to convert to scalar. uh, you know so these processes can be mathematically done, very carefully mathematically done. You can convert all this theory of everything, that equation, into a scalar form, and then you can measure the string theory. Same I don't know whether string theory we can convert into a scalar thing to measure them. I'm not sure, because it's so complex with dimensions and everything. But the concepts of the string theory can be used. That's what I'm using. They are very, very beautiful, very simple, very nice, because you have open strings, closed strings. That's it. So from that point of
Mm.
view, it's very
Well,
nice.
you're the first person I've heard say that string theory was very simple.
The
But I know what you
concepts, the
mean.
concepts,
I think you're just
the
talking about it
concepts.
on a basic level.
Yeah, the concepts are very simple, but the math is so complex that we don't know
Yeah,
what's going on. Yeah.
right.
So that's the
And
problem.
so you were saying you were talking there earlier about loop quantum gravity. You've got well, what I've heard about loop quantum gravity is that it is attempting to do away with the space-time metric
Yeah,
because there was problems there. So they thought, well, what if we get rid of space and time? So their
yeah.
solution to that, Lee Smolin's work, was to suggest that space
No,
is
yeah,
like emergent from a network.
yeah,
Um, I'm not sure if that's similar to spin networks, which is another kind of term
yeah,
you hear a lot of, but haven't
yeah.
really. I suppose maybe you could have symmetries within networks, and when they spin, they come.
Mhm.
We have again a Lagrangian from that or something.
Yeah,
But yeah, I mean, most of these things seem to be dealing with Lagrangians. So you'd have a tensor with these basically essentially gauges in them, like e to the I,
yeah.
you know, and
Hmm.
then and then you have another sort of vector that, and within those vectors then are further tensors, like smaller,
Oh,
let's
yeah,
say 2 by 2 matrices or 4 by 4, the gamma matrices. And
yeah,
then I think they have to commute with the other tensor. So And then if they do, they interact, and if they don't commute, then they don't interact. So that seems to be how it works.
Yes.
But that's it's interesting. So that seems to be that's like there's the gauge part of the Lagrangian, and then there's there's the Lagrangian part. And then I think they both somehow add together to become like the total energy or something, which seems different than a normal Lagrangian, which has the potential. So I assume one of them has to be the potential and the kinetic. So I've been working been looking into that quite a bit, because I think you recall from previous weeks I did work on the leptogenesis concept using the I Ching. And what I found is that we found a total of 8 new particles. So over the course of the week there, I just was working on it, and I was just calculating the masses of those particles, because all I had was the charges to begin with. And so because the masses, because the particle switches between charges, it oscillates charges as it moves through space. And because the charges are linked to the masses of the particles, it means that the particle also has to oscillate its mass. And yes, there's a couple of other things. So I was trying to work out different sort of Lagrangian calculations for them. And I worked out the Planck's quantized spectrum, the ultraviolet catastrophe. But then I think that's for light, though. It's for massless particles. And I also worked out the Yukawa coupling, which is for massive particles, but I think it's only for the weak boson. So I go through, like, these particular things aren't that complicated. Like, they're only a couple of lines of code. Some of them like just 3 or 4 lines. But I suppose it's the rationale behind them. Like, the rationale behind the Planck's quantized spectrum equation is very opaque. How it's actually how you would derive something like that. How you come to that conclusion, the answer, to use the Boltzmann equation as some sort of partitioning function or something. And yeah, it's just very strange. But yeah, so I can't really use any of it either at the end of the day, because the particles aren't massless and they aren't weak bosons. So yeah, it's kind of, well, I suppose I can use the Lagrangian part, but even that, I think, for a massive particle, it starts getting a bit funky on the quantum mechanics side of things when you're trying to do a Lagrangian, because there's it goes to infinity for large n, whatever it is, the quantum number. And so you have to do some sort of renormalization. And then there's another factor that, in general, when you're working with these, like, momentum equations, or it's 1/2 mv or squared or whatever, that's all for non-relativistic particles. So to have for relativistic particles, then particles that are moving at or close to the speed of light, you need to include things like the Dirac equation and other things. So I think at that point it gets a bit more complicated, but I probably need to go that distance, just because the if we're dealing with high energy physics at the beginning of the universe, everything's going to be knocking around very, very fast, So the particles are going to be zipping along. So if you were to do any sort of Lagrangian for whatever reason that you'd want to do that, so I'd have to employ these sort of Dirac operators and things of that nature. So I don't know if you have do you have much knowledge on that front? And then there's the issue of the renormalization, which I think comes through. That's a lot to do with Feynman path integrals or something. That might be a different. I know there's 2 different things that are kind of competing between path integrals and something
Yeah.
else. I forgot what it was. So so anyways, maybe QE. No, it's not QE. So yeah, I mean, so you can definitely renormalize those things, but I think you can also just renormalize the masses as well. So, well, might be worth looking into at another stage. I don't know if you have much. I mean, obviously you've used the Dirac equation. I know I have to some extent, but I'd have to go back
Mm.
and dig that out
Yeah.
because it's been a while.
So
Okay,
one of the
well,
things,
that's good. And
so, yeah, one of the things,
oh yeah, so
if you
what
have
about
chance,
the? I was just going to ask about. Um,
okay, okay.
there's another aspect there that we didn't touch on. Where we're talking about the network, spin networks, and all that. But what about are you going to go into Wolfram's work, or which is in category
Well,
theory, is
the
it?
next little more next, next two episodes will go into M theory and all that. I think I will touch
All right.
upon that, but I'm saying that one of the things I have the references, all this Wolfram and also Lee's morning that you talked about. I have reference. If you have a chance, we can go over them. They're quite interesting. I scanned through that. I didn't have a chance to go into all the details, but some more things caught my attention. And also
Mm.
another one is the thermodynamics. I again that's in the reference, the 3 page.
Oh
I
yeah.
believe the reference. And finally
Okay.
the Tong, the Cambridge professor, Professor Tong, he has extensive thing, but he talks a lot about the monopoles itself, but he goes into each aspect. He has sections on each aspect, and the math developed briefly, and that's something we can go through because what you're talking about, a lot of he touches upon a lot of those things. Uh, but and to come up, I think that's how we come up with the. Remember his famous lecture, the YouTube about the theory of everything, uh, that I really like, overall presentation, and he gives the equation and everything. That was like a couple of years ago, I think. We went through some of, and that's very important YouTube video. So you know, because I don't see the problem is I'm trying to filter out the math. The math really get to me, and you need generations not understand that math. So I'm trying to see how we can short circuit, not short circuit, but how to reduce those kind of math to more meaningful in terms of concepts and then develop the applied math, simplified math to understand the same thing. I think we can because remember that this Newtonian thing is still okay for mesoscopic. That's one thing we can keep in mind. Still okay for mesoscopic level. Everything works fine. But only when you go into detail about this aspect of you know, the ultraviolet catastrophe, things like that, that everything falls apart. And the gravity also falls apart for certain conditions, but mesoscopic level is fine. All the Newtonian, Galilean things are fine. So that's something we have to always keep in mind. And in many of my recent papers, I say how that I can develop, how it reduces to the classical aspect from Lagrangian and everything. And it also adds new things, little extra things which are very important. We can, I say, for example, once I said that if we keep a pendulum in an isolated situation, it has it has a noise medium, the supernova thing underneath that. You keep it for after a long time, the pendulum starts oscillating. That will be very interesting thing if you can do that. That proves
Well, you'd have
the
to
thing.
isolate it, wouldn't you, from everything?
Yeah, you have to isolate because we don't want winds, we don't want other things to disturb them, right? We don't want
Mm.
the normal things that's going on, pollution or other things. So you have to isolate that. Probably in a vacuum chamber if it's possible, or something like that. But keep the pendulum down there, and after a long period, I don't know how long. That's something I had to calculate. That math is again highly involved, but it may be like decades. We have to keep it decades even, and after a
Yeah.
few decades, it will start oscillating because because of the Lagrangian. I developed the Lagrangian. The Lagrangian says so. This balances, but after some time, what happens? The distorted field, it's quite simply put, the distorted field occur at the bottom of the pendulum, as you know, the curvature and all those things, the gravity. So you have distorted field, and it's a vortex thing that's happening, and that starts
Yeah.
moving. You need only very little energy, right, to move the pendulum. So that creates a kinetic energy, to say, to overcome the potential energy ever so slightly, that the pendulum starts oscillating. So that's the most deepest theory, and also a proof without doubt about the superluminous thing, and the condensation, and how the distorted field occurs. That's the final proof, and may even prove the discontinuum theory. In some sense, with the Emery Taylor, and you are probably many of your research, uh, predictions also, probably point to that. So that will be one experiment. There's another experiment I don't remember, but I talked about earlier in the earlier episode, with especially with Emery also. Those two are the key experiments to prove our things. So then it proves without any doubt that that's what is happening. And now, uh, as you see, I didn't have a chance to go through the complete thing, but Emmanuel is proposing a experiment he want to do in LHC, I think, about dark photons to prove the superluminous thing. So that's another thing that will be quite interesting. Uh, Dark photons that connects to gravitons and all that is
Oh yeah.
is the most recent. Yeah. So, and he has proposed experimental tech. He has given a design of the experiment to conduct, to do that. So that will be another interesting aspect, I think, of the thing. So experiment. I think, we will eventually, once we figure out the math, as soon as, I want to, and that code, I believe in the code that, thank you, and I could use the Python. Hopefully I will get a little more familiar with that, how to manipulate the code to get what we want. Then I think we code them. I think we can start simulating them, and you combine with your spatial thing, and the temporal thing. I am developing the time aspect and space aspect. You combine them, both of them into the same code. It will be complex coding, but I think we can probably do that, and that simulate the whole thing. And then we can then design experiment to prove them. After that, for example, the monopoles still are difficult to prove, but I think Tong also, concentrates a lot on the monopoles. Every chapter he talks about monopole, Dirac monopole, and he believes, I think, and I believe finally, I think monopoles will be the essential feature of the energetics. I don't see how the energy of the universe can be created without the monopoles. I don't see that. The modulations and things like this from the noise level. Um,
Okay.
so the
Yeah.
monopole is the one, like I'm talking about here, the I call the carrier wave the noise level, but the spikes are created by these monopoles most likely, and they are the ones that modulate, that creates the real universe, uh, because the monopoles, you know, they're probably sipping at superluminous speeds all the time, monopoles, but at some point they get locked in, because as we know, the monopoles become dipoles. Gauss theorem says that they had to become dipoles. So at some point they get locked in, and they form the horde or whatever, the dipole, and then that then creates the magnetic field and the electric field, and that creates the electromagnetic things and things like that. They develop from there all the way to gravity and strong nuclear, weak nuclear, and all that. But I think the monopoles are critical, and even Grand unified theory also predicts that monopoles had to be there. Without that, you cannot explain a lot of things, the energy aspect of the universe. And the monopoles are probably dark. So that's why you have dark energy, dark matter, because monopoles, when they are just monopoles, they are not observable. So they are dark. But when they form dipoles, they form magnetic thing, and the magnetism, when it is dynamically rotating, it creates electric. So you have electromagnetism, and that is light. That's when we can observe them. So the monopoles by themselves are not observable. They are dark. So that's why dark energy, dark matter eventually may be monopoles after all, in the most fundamental levels. So, those are things, of course, we have to prove. Those are the concepts that make sense, but without proof, we cannot say for sure that's the case. So that's the situation we are in. As we, move along each history, all that history is doing is that moving it in the way we know, whatever know-how, whatever knowledge we have, we are moving. We are not speculating anything in them, not in each episode. But then we move along. Uh, so if there is a doubt, you can always go back to the previous episode, and that tells what it is, right? So it's all I'll go step by step. I'll go history, how it developed, and so we have a way to go back and forth. Every time we have doubt, and I believe in you and myself. One of the things that people don't, one of the things I will have, if you have a place like Rider House, any place we discuss with people, one of the things I would say is that people, even if it is very simple, people have to define what it is. If I'm talking about placket, oh, you give me to talk about placket. What is placket? Tell me. I mean, each time they have to define briefly, maybe one sentence, maybe up to a paragraph, what it is. Anything that is out of the ordinary. Anything out like speed. I don't think everybody knows what speed is. Everybody knows kind of what momentum is. But even then, it's you know, good to say, okay, speed is the rate of change of, distance, for example. It's good to go to the most fundamental thing and give a definition or a legend that you can refer to, even though, you are supposed to know those. No, if you are talking about complex thing you're thinking, you sometimes cannot remember all these things. So I believe in that. That's one thing I would emphasize once we have the World Conference. This that people should go back in math or in physics. You develop that. What is Dirac monopoles, what they are. You have to give a brief description of that every time. Every time, describe that. And I also emphasize a very same thing. Uh, because we have to talk about DEF. We talk. I say it's good, if I talk about that, okay, discontinuum energy field. Oh, okay, what is that? So brief discussion of that. So every paper should have that kind of thing. It goes lattice group theory. What is lattice? Some people may not know what lattice. It's a very simple thing, but still give that simple definition. Like you cannot always refer to dictionary, or sometimes may not be exactly there. Wikipedia also goes through a lot of ramblings, so you may not get that. Give that simple definition, one page or one sentence, or which will clarify. Oh, then I know what it is. I can relate to that. So that's something I would suggest. People to really always go back to first principles or fundamentals. Even simplest things should be defined. Even simple equations should be defined in some ways. So actually, my Professor Kenny used to always say that. That's how I remember that when I go into the math and quantify, sometimes I don't. He said always give definition, even though it's very obvious, evident. People should know. Even a high school student should know. Even that you should describe. So I think that's a good idea. That's one
Oh yeah.
suggestion I have.
Well, yeah,
You
that
know.
is interesting. I mean, you hear a lot of talk about lattices, but and I'm kind of confused. I think Gerd does a lot of work, or he's done
Yeah,
work with
that's what I
them.
was trying to say. You put it right on there. Gert's work is based on this crystallographic, this lattice thing. It's very close to the lattice,
Hmm.
understanding of the lattice. Yeah, that's right.
Right.
So I
So,
think,
but there's things about the lattice. I mean, obviously, if you
yeah,
have well, how to phrase this? You have like a particle in a box, yeah, and you
yeah,
want to figure out its mass.
yeah,
Then so you could say, well, and then you maybe you want to extend that then like across space. So
Uh-huh.
instead of having just a box, you have like a grid of boxes, maybe.
Ah,
And so maybe that is what the lattice is it?
ah. In a
That's what
way,
I'm
but it's
thinking.
not exactly the definition. The original definition of lattice network is, for example, how the atoms are arranged in a like a BCC structure, like a body-centered cubic. You have one in the middle, then you have all the sides or the sides of the corners of the boxes. You have atoms there. If you have three, so each
Yeah.
corner of the lattice has an atom, and then you have an atom in the middle. They are all arranged equally, so it's like a cube inside a cube, and that is an example of a lattice. So there,
Oh, I
everything
know
is repeating.
I know
You
what a
know,
lattice is, but
yeah.
the question is, well, obviously in lattice QCD, it's being used to figure out the masses of the
Yeah,
quarks.
yeah,
Yeah.
yeah.
So presumably it's doing that well through some sort of well, I mean, if you think about it, well, you have lattices in string theory as well, bosonic
Hmm.
string theory. And
Hmm.
in that case, what that does is it allows you to calculate the ground state of bosons in bosonic
Hmm.
string theory. So, okay, so you have this method to do that. Um, but like, so that's different then to the mass side. If you're
Hmm.
calculating the ground state of something, right? So
Hmm.
um, presumably it's about partitioning space. So a bit like what we spoke about before with the Boltzmann constant and the quantization of the ultraviolet spectrum. So essentially, I assume the lattice is just about quantizing the field
Hmm.
into particles. So you're
Hmm.
you're partitioning the field, and the smaller you can get the lattice, then the more accurate your measurements will be.
Hmm.
Soon, presumably, then you have to do some sort of differential, calculation across the lattice, to
Hmm.
get your results, which will always only be an estimate, right?
Hmm.
But I mean, that's kind of how I see it. But I mean, you could. I mean, so the even the torus is then in string theory, where the strings are wrapped around these torus thing. They are
Hmm.
just they become a lattice. So
Hmm.
yeah, I mean, it's a bit strange that way. Um,
Yeah. Essentially, lattice, you can think of the simplest way. If you one or two sentences is a repeating pattern. That's it. So what that pattern is that if you have each pattern, you can think of a box, and in that box you have certain amount of entities in them, right? And these entities just repeat over space, over all of the space. So suppose I have a box, I have three particles in them, and I create the same dimension of the boxes, repeating, right, in a three-dimensional space. And then each box will have exactly three particles or three entities in them. So that's what
yes.
a lattice essentially is. In the
Oh,
simplest
okay.
way.
So
Mm.
it's right, but why would you want to do that? Well, why is what's the significance
Because,
of?
yeah, so suppose I study that one box. Now everything else is just a multiple of that, right? I understand all the properties, everything of that one box. Then I can just globalize the whole thing because they are all repeating the same thing, except I have to know the interactions, but everything else is the same. the particles, how they move around, the three particles, how they move around, how they are arranged together. It's exactly the same in all of them. So suppose the distance I calculate, the fields, the charges, the mass. Suppose I know the mass and everything, so I can calculate charge, mass, the field, all those things for one box. And all I have to do is in every box is repeated. Now I am assuming they're isolated. Of course, they are interactive things. Like when they connect, you have to see the coupling or the interactions. That's an additional thing you have to calculate. But for all practical purposes, like in atom, like in materials, we talk about crystals, like BCC, like I said, has
Yeah.
the atoms in all the corners of the boxes, the cube,
Yeah.
and and an atom in the middle. So suppose iron is, iron has a structure, FCC structure, a face center also. Then and carbon comes and then create and then comes in between them, right? So they created something called body centered tetragonal. So they create the stress. So you can calculate the stress when the carbon is become interstitious, and how the carbon acts and how it strengthens the iron, because iron by itself, very pure iron, is very very weak, right? But the carbon is
Ah, right.
incorporated, they become strong. Yeah. So this is
Yeah.
described how nicely how the stress is coming up based on this lattice, based on the cubic structure. When iron goes in the interstices, they create a stress, right? They pull apart the things, but they arrange, they
I
relax
suppose
to a state.
that's a slightly different discipline, Rajan, with the that you're discussing there with the crystallography or whatever. But
Yeah, yeah.
yeah, I mean, for sure,
Based on that,
I
it's
mean, it's
also
interesting
see.
the point you made earlier about the repeated boxes where you just have like a
Yeah,
maybe
yeah,
a random
uh,
sample of particles in there,
yeah.
because that's interesting that you should mention that, because that is exactly what I'm doing in my own work on the
Okay.
we're with the particle simulator for leptogenesis. I just have a grid that's like 100 by
Uh-huh,
100, and then
uh-huh,
I throw in maybe like 96 particles, which are just the same six particles repeated over and over again, and then they all
uh-huh.
interact, and then
Okay.
you get you get your results, like how many particles come out of the
Mm-hmm,
interactions at the end, and what's the lepton number, or whatever, you
mm-hmm,
know. So then so yeah, you could just I suppose you could technically repeat that then over a volume. I'm not. I mean,
yeah.
I suppose that would be sort of useful. You know, I mean, maybe you'd use some calculation like Monte Carlo or simulation or
Mm-hmm.
something. Maybe that's what that's about. So I suppose that'd be more useful, and in a practical sense, like in a nuclear reactor or something. But I
Oh yeah,
suppose for a less you know, for something that we'd be working on, more theoretical kind of
yeah.
research, the boxes need to extend across the entire universe. So at that
Yes.
point, it becomes futile to yeah, to
Yeah.
differentiate or to generalize over all of these boxes. So
We don't know it.
in that
That's what
case,
I
you
mean.
might as well just stick to like one box, unless you have a way of reducing the size of the universe, you know,
Yeah.
in some mathematical way, like the way the anamorphic universe model hypothesis
Uh-huh.
does that I've been working. That reduces it considerably, although we're still um, we're still a bit of ways off to actually calculate that. You need to get the right software for that. So,
Yeah.
but
See, when I'm considering
should
this,
happen in the
right?
next couple months.
It's interesting that I was thinking about your idea, your famous the model of OM that your
Yes.
tangential plane and the the hyper dimensional plane is very
Yes.
similar. It has some connections to that because the real world is on the tangential plane. So you have the already vector degraded, the tensor degraded tensor. So you have
Huh.
lower rank tensors in the in the in the tangential plane, and you have
Right.
higher rank tensors in the hyper dimension. So that seems quite fundamental, you know. So when we
Oh,
combine that,
interesting.
those are something, yeah, those are something that we may have something in common. So I'm seeing the common
Yeah,
area,
that's it.
you know, that the
And then of
time
course,
space.
you know, if you are able to like, you know, if you have like a something like that you're working on, yeah, that's interesting
Yeah,
because I mean, yeah,
yeah.
it's a funny thing because how is the I mean, obviously the sphere itself would have well, I mean, the mapping from the sphere to the plane would imply some sort of tensor, but we can kind of get away without using one. Initially, I was thinking that I would have to, but if you're talking about, yeah, I think because there's an idea that there'd be the physics on the sphere would be sort of different to the physics on the plane in some sense.
Mm-hmm.
I mean, they'd obviously be like want to be identical, but you know, like for instance, some like the idea was maybe that some quantum
Mm-hmm.
effects would occur on the sphere and not on the plane. But
Ah, okay.
yeah, it hasn't really been worked out yet. For example, like all the thing about I did a lot of work with quaternions and particle um, geometries, let's say,
Mm-hmm.
and what I found was well, a lot of that stuff I was able to just like reformulate, maybe spin one half into
Mm-hmm.
a four-dimensional rotation. So there's a lot of work where by just adding an extra spatial dimension, you would get a, a lot of the same kind of results as you might from a 3+1
Mm-hmm.
or quantum field theory analysis of the same thing. So the
Mm-hmm.
idea is then, well, is the reason for this because of this four-dimensional hypersphere? But no, it doesn't seem like it because for the surface, obviously the universe exists on the surface of the hypersphere, and that's still three-dimensional. It's curving in a
Mm-hmm.
four spatial dimensional
Mm-hmm.
space, but it's not
Mm-hmm.
actually four-dimensional in a sense, you know, any
It's
more than a
medium,
2D plane
medium.
that's slightly curved
Mm-hmm.
is a 3D surface, you know.
Mm-hmm.
Anyway, I think we went over a lot of stuff there, and thanks for
Yeah,
your
yeah.
presentation.
Thank
But
you.
yeah, I think we should we'll leave it there, and we'll come back to it next week, perhaps.
Next week,
Oh
yeah,
yeah.
yeah, yeah. Excellent
Okay, so if
discussion,
you
Christopher. I enjoyed your, very detailed discussion and debate because it throw a new light, completely a deeper understanding of the whole thing. I think we are coming closer to getting somewhere. We are integrating our knowledge to really solve the real problem. I think I have more and more confidence as we go along. In that thing. So thank you very
great,
much.
yeah. Okay, if you want
So
to,
yeah,
or if you want to go ahead and end this the
and the
stream,
stream.
then
Okay.
yeah, because I don't.